did at Data Artisans. Basically, this is a runner for cascading jobs on Apache Flink. So first of all, for everybody who's not familiar with cascading, cascading, as it quotes itself, is the proven application development platform for building data applications on Hadoop. So essentially, it's a Java API for large-scale batch processing. The programs are specified as data flows, and this is also reflected in the terminology which is used within cascading. So you'll find something like pipes, taps, flows, cascades, and cascading comes with a couple of operators, such as each, which is kind of like a map function. It has a group by, every, co-group, merge. So a lot of the concepts that you also know from frameworks like Spark or Flink. And a lot of these have to be implemented. If you want to run this on MapReduce, you have to implement it yourself. Cascading is open source. It's open source under Apache license and developed by Concurrent. Originally, cascading was built on top of MapReduce. So it offers a much better API than MapReduce. So it comes with a DAG data programming model. So you specify your programs as a DAG of operators. It has higher level operators such as join and co-group, something that MapReduce doesn't offer. It has a tuple-based type system where MapReduce is kind of like limited to key value pairs. And when you implement your programs as cascading programs, your code is reusable. You can recompose certain parts. So this makes altogether, this makes it a better API than MapReduce. And when you implement a cascading job and you want to execute it on MapReduce, this program is automatically compiled into a sequence, into a workflow of MapReduce programs. And the compiler works in a way that it tries to minimize the number of MapReduce jobs. So if you're familiar with MapReduce and have been writing more complex applications with it, you know that the number of MapReduce jobs kind of like has a big impact on how the application will perform. So if you have many jobs, the application will be pretty slow. And the whole execution is rock solid because it's based on Apache Hadoop. So Apache Hadoop may be slow in some cases, but it's rock solid. If you start something, it will continue and it will be finished at some point in time. So this basically makes cascading like a workhorse for many environments. It works reliably, but maybe not in the fastest way. So this is an example that I took from a cascading programming guide. So this is from the cascading for the impatient. This basically shows how to compute a flow that computes the TF-IDF score. So for everybody who's not familiar with TF-IDF, this is kind of like a rating function to rate the importance of a word in a document collection. So this is used by search engines, for example. If you type in your search query into Google, then Google basically needs to identify which words are the most relevant in certain documents. And if you look at this flow here, you see that there are a lot of operators. There are branching flows, merging flows, and so ever. And if you want to implement that on top of MapReduce, this is going to be pretty painful. And with cascading, you more or less plug this flow together, and then this is automatically compiled into a sequence of MapReduce jobs. So who's using cascading? Cascading is used by quite a lot companies in production environments, including Twitter, SoundCloud, Etsy, Airbnb. And some of these companies also put more APIs on top. So cascading itself is an Java API. And Twitter, for example, put a Scala API on top of that, which is called Cascading. There is a data log API called Cascading, which has been started by Nathan Martz, which is kind of like the head behind the Storm project as well. There's a SQL on top of Cascading, and also like a more fluent Java API called Fluent. Cascading 3 is the latest release of Cascading. It has been released in June this year. It includes a new planner, which basically means that the execution backend can be changed. Up until that point, Cascading could only run on MapReduce, MapReduce version 1 and MapReduce version 2. And this release also included a test backend, which basically means that Cascading programs are not compiled into MapReduce jobs anymore, but instead into test programs. And by avoiding the compilation to MapReduce jobs, one could get rid of artifacts that come with a very strict MapReduce programming model, such as the identity mappers, and there was no more writing between certain parts of the job, because one MapReduce job ended and the next one started. So in MapReduce, you usually have to write into a persistent file storage to get the data across one job to the next. Okay, so much for the introduction of Cascading. So first of all, why is it a good idea to put Cascading on top of Flink? This is basically because of Flink's quite unique runtime. So the Flink runtime has some very nice features, including the pipeline data exchange. So not doing batch transfers, but instead pipelined data transfers between operators. It also comes with this actively managed memory, and the which can be done on heap and off heap. The very efficient in-memory operators that spill to disk if memory is short. A lot of operations in Flink happen on binary data, so including sorting and building hash tables. And this actively managed memory also avoids a lot of tuning knobs that you need for other systems. So it provides a very robust execution backend without the need for very fine-grained parameter tuning. And last but not least, Flink also has a very nice yarn integration, which lets you allow to run Flink jobs very nicely on a yarn cluster. We released Cascading on Flink about 2 weeks ago. It's available on GitHub, also open source under Apache license. And it depends right now on 2 snapshot versions. So it depends on the Cascading 3.1 work in progress branch and the Flink 010 snapshot branch. So since both dependencies are a little bit in flux, this makes it sometimes a little bit tricky to keep up with all their changes. But once Cascading has a new stable release out and Flink has a new stable release out, we're gonna fix these dependencies for the Cascading planner, and all these shaky APIs will be gone. So this is the repository down here. So it's in the Data Artisans GitHub repository if you want to check out the code. So now I'm talking a little bit about the internals of the translation process of how Cascading jobs are translated into Flink programs. The whole translation process is implemented on top of Flink's Java dataset API. So we're using here the Flink's batch API. And we're also using Cascading's rule-based planner. And we implemented the translation rules in a way that a Cascading flow is translated into a single Flink program. So no more different jobs that need to be coordinated, but instead one single job. And the operators within the Cascading flow are kind of like grouped together, so we can into so-called nodes. And the reason for that is that very efficient pipelining can happen within the operators within one node, so there's no they don't need to switch a context here. the translation routes are written in a way that we have to create a new node, like a new group of operators, whenever data is shuffled, whenever data is processed by Flink's internal operator. So we kind of like need to get out of the cascading context and put some data into the Flink context for processing. Whenever flows merge and branch, you've seen cascading offers a DAG programming model where the flow can branch and merge together again. So whenever that happens, we need to break the code into independent nodes, and also at the sources and sinks, because Flink kind of like demands sources and sinks to be in their own group. Cascading operators have kind of like a fixed execution strategy in there. So they, when you have a cascading operator, it kind of like dictates how it wants to be executed. For example, a co-group in cascading is always realized using a repartition strategy, which shuffles the data and sorts the data. So it's always a sort merge co-group. A hash join is always realized as a broadcast hash join variant with a smaller site. So the build site is broadcasted to all other sites. So this basically means that there is no degree of freedom left for the Flink optimizer. So the Flink optimizer has by the semantics of the cascading operators, may not choose the execution strategies, but instead we have to tell the optimizer which execution strategy to use. When we say do a join, then we have to say please do a hash join with broadcasting this side. Most of the cascading operators are translated directly into Flink's native operators, which basically means that a lot of the logic is taken, that it would be executed in cascading scope in MapReduce, is being executed within Flink after this in the Flink cascading translator. Talking about serializers and comparators, so whenever the processors need to exchange data or write data into memory or to disk, we need serializers. Flink needs this information before the program is executed, so we need information about all data types that are processed within a cascading program, and Flink needs that to generate appropriate serializers and comparators for these data types. Cascading supports a few things which make that a little bit tricky. Among these things are schemaless tuples, so tuples with unknown length and unknown type information. It also supports definition of key fields by name, which Flink also does, and by position, which Flink also does, but it also allows relative position. So for example, you can say I have a tuple with unknown length, and I want to group it on the second last field, which is a little bit was a little bit tricky to get into Flink. And finally, it also cascading also supports null-valued fields, and also grouping and sorting, or using null-valued fields as keys, something that Flink also doesn't support out of the box. However, we could put that into Flink by actually implementing our own custom type information, serializers and comparators. So Flink is has a very, very good interface to plug in your custom comparators and custom serializers if you want to do that. So this is kind of like an advanced API feature, but if you know what you're doing, you can tweak the system in the way that you want to, and also support like null-valued keys, for example. In our implementation, we use Flink's native serializers and comparators for everything that is for all data types which are known, and Java primitives and strings. And we also identify data types that implement Hadoop's comparable interface. So we know the Hadoop's writable comparable interface. So we use these the serialization logic, which is basically implemented in these methods. For all fields that we don't know, we just use cryo and serialize the data with cryo. Talking about processing data out of core. Basically, join and co-group operations require, or at some point in time, need to hold data in memory for either you build a hash table, or which you should put into memory, or if you're running like a sort merge join, there might be a situation where you have multiple keys on each side, and you need to build a cross product. So you need to put some data into memory. Cascading on MapReduce realizes that with spillable collections. So basically there's a spillable list, and there's a certain threshold that you can configure, and whenever, let's say the list has more than 1,000 elements, it starts putting elements to disk. This is also part of the cascading code. This is not part of the MapReduce code in this implementation. And the tricky thing is, how do you set this threshold, right? So if you set it too high, your job gonna die with an out of memory error. If you set it too low, you might not leverage the full memory. So it's really hard to set. It might also be very very dependent on the data. If you have data skew, you have to play safe, and so on. So getting these parameters right is a hard thing to do. And if you want to play safe, you probably have to sacrifice performance for that. In Cascading on Flink, joins and co-groups are implemented using Flink's own native join implementation and auto join implementation. And these operate on Flink's managed memory. So these algorithms basically receive a certain budget of memory, which they can use to put data into memory. And once this budget is exceeded, they start spilling data to disk. And all of that basically happens automatically. You don't have to configure any thresholds when the system should start to do that. You just configure the amount of memory that should be available for Flink when processing data, and then Flink will assign memory to operators and also take care what happens when you run out of memory. Okay, what do I need to do to use this Cascading on Flink runner? It's pretty simple. You basically have to add the Flink Cascading Maven dependency to your Cascading program. It's available in Sonatype. However, it might get outdated. As I said before, we are operating here on 2 work-in-progress branches. So it might be necessary that you build it from source. The source is on GitHub. And then all you have to do is basically just switch one line of code. So you basically only have to replace this so-called flow connector, which is basically compiling the cascading program into a so-called flow, which then can be executed. And in case of MapReduce, there is this so-called Hadoop 2 MapReduce 1 flow connector, and this one you just replace by the Flink connector, and then we'll compile the cascading flow into a flow which is executed as a Flink program. This also means that you don't have to touch the application logic, so the cascading program stays exactly as it is. And you then execute the cascading program just like any other regular Flink program. So you can use Flink's command line client or the web submission client. So whatever tools you use to submit your programs. All right, here are some very preliminary performance numbers here. We did that on a small cluster of 8 nodes with 8 CPUs, 30 gigabytes RAM, and 2 local SSDs each. We did it on Hadoop with 2.7.1. We used Yarn at HDFS, Yarn setup with HDFS, of course, and MapReduce for executing the jobs with cascading on MapReduce. we used the current Flink master snapshot, and we generated a small data set of 80 gigabytes of text data. As a baseline, we wanted to check how does it perform the very, very standard word count. So we did that basically just to verify our own implementation, see how does it behave against the MapReduce implementation, how bad is the performance penalty of using Cascading on Flink versus Flink native and MapReduce native and so on. And we didn't expect like very, very significant speed gains here. There are some notable things here. So the Cascading implementations use hash-based combiners. So Cascading doesn't use MapReduce combined interface, which is sort-based, but it comes with its own hash combiner, and the same hash combiner is also used for Flink. You see here that basically Cascading on Flink is a little bit faster than Flink native, and this is also just because Flink doesn't have a hash combiner. It also does sort-based combining, and this is why there's a small performance improvement for Cascading in Flink. Yeah, basically this kind of like shows that our implementation is not performing too bad against neither against Flink native or the Cascading on MapReduce. We also tried something a little bit more complex, which is this TF-IDF example that I showed before. This program here consists of 2 co-groups, 7 group bys, and 1 hash join. And if you run that on MapReduce, this will be compiled into a total of 9 MapReduce jobs here, which have like a few dependencies. And each of these jobs reads data from HDFS, gives it to a map function, shuffles it over the network, sorts it, applies the reduce function, and writes it back to HDFS. So all of this happens in total 9 times for each of these jobs. Some jobs read more data, other jobs read less data because it has been pre-aggregated, but still it's 9 jobs that need to be processed. For executing the whole thing on Flink, we get 1 job, which is this giant egg here, which basically contains everything. And if we look into that, the Flink plan or the Flink execution plan looks like this. And if we compare the performance here, you basically see that we get a speed up of a factor of 2.5 compared to the MapReduce numbers. And this is mainly because we don't read we don't write data to HDFS. We don't read it from HDFS again. The shuffles are pipelined. And we were running on Flink's native operators like hash join and so on. Okay, to conclude, executing cascading jobs on Apache Flink improves the runtime, at least for the few examples that we evaluated. It reduces the parameter tuning and avoids failures because you don't have to really tweak your parameters. How much can I set this spillable list threshold until things break? What happens if I use a new data set and so on? So all of that is basically, you don't need to worry if you're using Flink because Flink's operators handle that by themselves. And you don't need to change your code. So except for replacing this one, basically the flow connector. And it also shows that that you can put a lot of things on Flink's runtime, right? So we have by now a connector for Apache Hadoop MapReduce. There's also a connector for Storm, which is a streaming system, Google Dataflow, Apache some more, Apache's Flink own API. So we got a wild mix of different batch and stream processing systems, which can all basically run on the same backend. Thanks. Questions?
I know there was like a separate talk on Spark versus Flink, but just to get another idea for TF-IDF and another benchmarks that you
Sorry?
The TF, IDF, and other benchmarks that you compared. TF, IDF,
Yes.
and other benchmarks that you compared. You mentioned that the majority of performance gain that you are gaining against MapReduce.
Again, yes, that's right.
It's because of you are avoiding the shuffle writes in disk, right?
Yes.
So if like similar system like Spark, right? Spark also avoids the disk writes. So if you compare Flink against Spark in specific those benchmarks, so have you done the comparison or is it like?
There is no cascading on Spark that I'm aware of.
Yeah, but like native implementations as well. Like
Native
for example,
implementation, no.
Okay.
My question is on, you have implementation on cascading. What about how difficult it will be to do the same for scalding?
I don't know. As far as I know, scalding basically compiles into cascading. So it would be like put one on top of the other. I just talked to somebody else who tried Cascalog with this adapter, and it failed because the data types couldn't be serialized using cryo. So we use cryo for this generic types if we don't know how the tape looks like. Maybe we're a little bit lazy there, just using cryo for everything that we don't know, and can try to get integrate with cascading serializers a little bit better here. It might work, putting scalding on top, but I'm not aware of anybody who's tried that. So you might be the first. And I would be, if you tried, let me know.
Did the implementation here use Flink's sort of type, I don't know what you want to call it, type inference that it has in order to do the shuffle and all this efficiently? Or was it sort of the default path where you say, oh, I don't know enough about the types? And
so the type extraction, or are you referring to type extraction?
yeah, exactly.
No, we basically hard-coded the types. So so we basically extracted from the cascading program what kinds of type we have available,
Yep.
and created our own type information that we again forced on Flink. So
Okay.
when we saw, for example, that there is a tuple int string in defined in cascading, we would use this information to create an appropriate type information that uses the integer and string serializers. But if there was just a tuple unknown, which would be of unknown length and unknown types, where you would create that into a type information which would basically serialize the length of the tuple and then use cryo to serialize all fields.
Okay. And secondly, did you, were there any like major challenges, or was it relatively straightforward to go from Cascading's sort of model into Flink?
Yeah, so one of the major challenges was to get into Cascading's rule-based planner. So mainly because it was not so well documented, and doing a lot of magic there. So, but once I figured out how to do it and what I had to do, getting the rules for partitioning basically the graph into a way that I can execute as a Flink program, that was okay. There also like cascading. So when you work with the cascading API, you basically feel that it's been inspired or put on top of MapReduce. So there are a few design choices which I kind of like had to more or less hack into Flink to get it to work. But yeah, it took me some time to get everything passed and the things. And then there are like things like this tuples of unknown type and null key fields that you kind of like have to support. So there are a lot of different features in this in cascading, which made it not so straightforward to get it to run on Flink. Further questions? Okay, thanks.